Hello and welcome to the first screencast of the semester, Anatomy and Physiology 1. This right here is the book we're using. Hopefully you have this one. So quick heads up, this is an open educational resource, which means it is not copyrighted. So all of the images that I'm using are not copyrighted. The imagery in all of my lectures either come from this book or some other non-copyrighted source. There are a few that I have forgotten to replace, but like 95% is not copyrighted. And that's just what this says. First up, and this whole screencast should be relatively short. First up, you just want to know the definition of anatomy and the definition of physiology. They're right there. I won't read them. And then you want to understand the principle of complementarity. As it says there, anatomy and physiology are inseparable. So function reflects structure, and if you're looking at the structure of something, you can maybe infer something about its function. And the other thing I will point out is that this works at all different levels of structure, as I will show you in just a moment. Who cares about this? All right, does anybody know what organ this is? 5, 4, 3, 2, 1. It's a kidney. Some of you may have guessed, some of you may have not. Do you know what the kidney does? It filters things. So it filters your blood, produces urine. This is a lymph node. Has a similar shape to a kidney, right? It's got that kidney bean shape. And if I ask you what it does, you might guess that it filters something, right? This filters the lymph. So it has similar shape to the lymph node, similar function as a kidney, so similar shape as a kidney. So where functions are required in multiple places in different parts of the body, shapes, and especially what you're going to see as tissues, are going to get repeated in different organs throughout the body. But it works all the way down to the molecular level. This is serotonin. Serotonin, among other things, kind of helps you feel good. This is, if you don't have enough of this is what causes clinical depression. This is what serotonin looks like. These over here are called SSRIs, or selective serotonin reuptake inhibitors. Their job is to stick to serotonin pumps, which actually clear it from the active regions of the brain, so it's sort of deactivating it by taking it out of circulation. And so what they're supposed to do is look enough like serotonin to stick to the pump, but not so much like serotonin that they actually get pumped, so they kind of clog the pump up. So you can see, right, they need to act like serotonin in that they need to interact with the serotonin pump, so they have similar structures to serotonin. Not so similar that they actually get pumped, but that's just one example. There are probably better ones I could come up with. But structure and function goes all the way down to the molecular level. And if you think about the body this way, then that means that it is a very complicated machine that runs on, yes, a little bit of mechanics and chemistry, but even chemistry, right, the rules of chemistry are written by physics. Physics is the laws that govern physical interactions of things and other stuff. So everything in your body is physical. It is all knowable. It is complicated, but nothing that defies understanding or explanation. Except for consciousness, that we don't really get. That is an emergent property, and emergent properties are hard to describe. So then levels of structure, this I want to do relatively quickly. You just need to know what order you're supposed to put the levels of structure in, and you need to know what's the word I'm looking for? Two definitions that I think are important. So one is cells, the chemical level, atoms, ions, molecules, we all get that. I want you to think of a cell as being composed of molecules, atoms, and ions. So level 2 is a functional arrangement of the stuff that you find in level 1. And then tissues are going to be a mixture of living cells from layer 2 plus non-living, what is called extracellular matrix. This will make a little bit more sense when we get into tissues, but if you think of like bone, right, a lot of your bone is minerals. It is calcium phosphate. Calcium phosphate is not alive, it is just rock. But there are bone cells, osteocytes, embedded in it. So bone tissue is this combination of living osteocytes and non-living bone matrix. So a tissue is a combination of cells and extracellular fluid. So it's this part right here I want you to know. And each tissue, as it says here, has a relatively specific or narrow set of physical and physiological properties. And the tissues we are going to see get repeated in different organs. So then you go to 4. 4 is organ. This is also, I'll circle that, a definition that I want you to commit to memory. I want you to think of an organ as a functional arrangement of tissues. Now, you don't know how many tissue types we have. I will tell you, there are 4 different tissue types in your whole body. But you have lots of organs, right? Heart, lung, stomach, kidney, liver, brain, spinal cord, muscle, bone, ligament. All those different organs are each different combinations of 4 different basic tissue types. The example they have here, right, this tissue type here is smooth muscle. So it's going to contain smooth muscle cells and then connective tissue that holds all the cells together and neurons and blood vessels. Then the next level up, this organ is a bladder. The bladder is going to have a lining on the inside of it called an epithelium, some connective tissue on the outside of it to hold it all together, and sandwiched in between those two is going to be our friend smooth muscle. Smooth muscle is also the type of muscle that you find in your blood vessels, which allows for vasodilation and vasoconstriction, and smooth muscle is what you find lining your gastrointestinal tract, which pushes the food along and squeezes off in different places to make sure that urine stays in your body until you're ready to get rid of it. So that's just one example of smooth muscle showing up in multiple different organs. And then this organ here, the bladder, being composed of epithelia, smooth muscle, and connective tissue. Then you get to the organ system, which I don't care you know the definition of the organ system, and an organism, and I don't care you know the definition of an organism. This slide, you just want to commit this list to memory. If we had more time and we were meeting in the classroom, we would talk about how these life functions map to your different organ systems, but it just doesn't work very well online. So commit that list to memory, and you can expect maybe some kind of question on the exam that says, which of the following is not a necessary life function? And you'd have to pick the one that's not on this list. So then we get to homeostasis. This is kind of the meat of this chapter. This is the most important part. Before we talk about homeostasis, we need to identify this term here, a variable. And as it says here, any measurable physical, chemical state or process within the body. So it's pretty vague. But for us, it's really anything about the body that's measurable that we care about. So this is things like blood pH, body temperature, your hydration state, blood sugar levels, insulin levels, all of these things are variable. Homeostasis is, as this says right here, the dynamic process of maintaining body variables within healthy limits while responding to external and internal changes and demands. There is a lot in that. Every word there is important. First word there, dynamic, that's important because it means, it's always happening. So you don't want to think of homeostasis as, a lot of term people sometimes use is balance. But if you think balance, think somebody walking across a tightrope, trying to balance across a tightrope, and their arms are waving and their legs are wobbly, right? It's a lot of work to keep your balance on a tightrope if you're like a regular person. So you're always adjusting for homeostasis. And the variables that we consider to be homeostatically controlled are the ones that stay within healthy limits. So these are things like your blood CO2 levels, blood pH, temperature, hydration. All of these things we want to keep in a relatively narrow range. And all the while, as it says here, responding to external and internal changes and demands. We will have some examples of that when I give you the exercise, the other thing that's posted up there in a minute. But just know that things inside your body and outside your body are always changing, so that your body is always having to do work to maintain homeostasis, or to keep the variables, certain variables, within healthy limits. Then we cover two important homeostatic control mechanisms. They are negative feedback and positive feedback. You want to know the basic descriptions of both. So I will just explain how this works, and don't worry about what's written down right here. In negative feedback, you have some sort of stimulus, which means a homeostatically controlled variable, like body temperature, moves outside of the normal range. Your body then responds. In this case, you've warmed up. Your body responds by sweating. When you cool back down, you're going to stop sweating. That's the negative feedback part, and that's what makes it so useful, is that your body is not just responding to changes, but it's setting things right, and then shutting off. It seems obvious to us, especially in today's modern world, because most things we use have feedback within them. Like the thermostat on your house, you set it to, let's say, 65 or 70 in the winter. When it gets cold, the furnace kicks on. When the temperature warms up, the thermostat notices that, shuts the furnace off. So you've got a negative feedback loop that controls your furnace and turns it on when the house is cold and off when the house warms back up again. Back in the day, if you had a wood-burning stove, right, if you put too much wood in the stove, your house would get hotter than you wanted it to be. And if you didn't add more wood to your wood-burning stove, your house would get cooler than you want it to be. So having a negative feedback loop is very important. And not, how should I put it? It's not something that's automatically built into everything. This is something that had to evolve. So the other things you want to know about it down here, right? It is the most common form of feedback because you want to keep most of your variables within a normal range, right? What this does is keep any variable from straying too far in either direction away from the homeostatically controlled set point. As it says here, keeps them in a normal range. So the variable that we care about, that we're regulating, is what is homeostatically controlled. So in this case, it is your body temperature that is being homeostatically controlled, and the amount you sweat is going to vary widely. Right? So you don't want your body temperature to change very much at all. So if you're exercising to counteract all of that heat you're generating, you are going to sweat a lot. So it is normal to have the amount of sweat that you're generating vary over a great range, because that's what keeps your body temperature from varying over a great range. And that is the homeostatically controlled variable. Next up is positive feedback. In positive feedback, you get a stimulus, but in this case there is no auto shutoff. It does not stop and usually tends to accelerate the response or a response to the initial stimulus. What they're showing you here is one of the more popular examples of it. This is childbirth. I believe in childbirth, the original stimulus comes from the uterus, and the uterus tells the brain to start making oxytocin. When oxytocin travels from the pituitary to the uterus, it causes uterine contractions. Uterine contractions push the baby further down the uterus, dilating the cervix. When the cervix dilates, that causes more oxytocin to be released. So the more oxytocin that you release, the more uterine contractions you get, which causes more oxytocin release and uterine contractions. So you can see this is going to accelerate until something big happens to disrupt the positive feedback cycle, and in this case it would be delivery of the baby. Platelet plug formation is another one. I won't go over it in detail because I don't have a picture for it, but basically what happens is platelets stick to ruptured blood vessels, and when a couple platelets stick, it attracts a lot more platelets, which then attract more platelets until the blood vessel is completely plugged up. So I'm going to pause it here and tell you that you should get these slides out, look over this, look over that, see if you can answer these questions. I have to make my screen bigger. And then when we unpause it, we'll go over these questions. Hey, we're back. I hope that was fun. So real quick, right, what we have here is two negative feedback loops. And you'll notice with these that they are double negative feedback loops, which is also a common homeostatically controlled mechanism so that you can keep something from varying in two different directions. So you don't get too hot or too cold, or so your blood sugar level doesn't go too low or too high. So what we're going to do is I'm going to read off these questions, but I'm just going to have this up on the screen up here, and that's what we're going to look at. So hopefully you've printed this out at least, or you've answered these questions, and we're going to go over it. So question number 1, it says, what is the normal range of blood sugar? Is there a target? And here is blood sugar normal range between 72 and 110 milligrams per deciliter. Normal, the target that your body is happiest with for most people, is 90 milligrams per deciliter. That's what 100 milliliters is. And if you get outside of this range here, that is when insulin gets released or glucagon gets released. So the normal range for insulin, up to 90 milligrams per deciliter and down to 5 milligrams per deciliter. So just to compare our range for insulin to our range for, range for blood sugar levels. So now we're answering the question, is the range for insulin bigger or smaller than the range for sugar? So for blood sugar, low is 79, high is 110. So 110 isn't even twice as big as 79 milligrams per deciliter. So 90 through 5 doesn't seem like a really big range, but 90 is 18 times bigger than 5. So because the low end of your range of insulin is so low, it's actually very dramatic. It's a dramatic change to go from 5 to 90. So you've got this wide range of insulin levels that exist that helps keep your blood sugar levels finely tuned and in this relatively narrow range. And I didn't look up glucagon, but I'm assuming also that there's a pretty wide range of acceptable glucagon levels. So again, just think about if you're exercising, your heart rate's going to go way up because your body has metabolic needs that your heart is helping to regulate. So it is normal to have a resting heart rate somewhere between 65 and 70. It is also normal for your heart rate to get up to 140 or 180. All of that is considered healthy, normal homeostasis. That's all so that your blood CO2 levels don't skyrocket when you exercise. What is our next question? What do you think is happening to your blood sugar levels as you sit at home pondering this stuff? Right? If you ate like an hour ago, right, your body has absorbed the sugar, and your blood levels, the longer you go between meals, they start to go down. What would happen to insulin levels if you just sit here long enough, right? If you, not doing much of anything, sit here and watch videos and check email and do schoolwork for 8 hours after your last meal, your blood sugar levels are going to start to get really low and your insulin is going to creep up. So even though you're not doing anything, right, parameters within your body are always changing because metabolism is always requiring energy. So you don't have to do anything really to cause your blood sugar to go down and, your glucagon levels to rise. Blood sugar down, glucagon gets released. Blood sugar up, insulin gets released. So then the variable here, number 5, that is homeostatically controlled, that is more tightly controlled, is the blood sugar. So blood sugar has a narrower range. That's the one that we're controlling by using insulin and glucagon. So we allow insulin and glucagon levels to rise and fall dramatically, and that's what keeps blood sugar in that narrow homeostatic range. And then I'm just, for number 6, the question, drawing the distinction between internal changes and external changes. So this is all responding to internal changes, and regulating your body temperature is an internal change, but the ultimate cause of said internal body temperature change is changes in your external environment. So when it gets hotter or colder. That's it. That's 22 minutes, and that's all you need to know for Chapter 1. Anything else in the book you can safely ignore. One more thing I just wanted to point out, right? Here are your objectives. Don't forget to have your objectives and you will notice you will notice that the PowerPoints go over the objectives, or go along with the objectives pretty well. This is what we covered. The only thing that I told you not to worry about is matching the life functions with the proper organ system. We will go over organ systems in lab, but we don't connect them to functions because we're really getting ahead of ourselves if we do every organ system. So that's it. See you at the next screencast.